everybody, and welcome to Taiwan Talk. It's a show where we explore news and topics from here in Taiwan. I'm today's host, Trevor Tortomasi, and for this episode, I'm speaking with Satoki Matsushita, an astrophysicist from Japan. Satoki has been based in Taiwan and abroad for many years while working with international projects like the Event Horizon Telescope and the Greenland Telescope Project. You may recall an orange and black picture of a black hole on the internet and all over the news a few years ago. Satoki was a big part of the project that created that image. And I have to be honest, while I was editing this interview, I was tempted to edit out some of my more naive questions, but I left them in for continuity's sake, so you'll have to excuse my childish glee as I pester Satoki with my curiosity. I was just way too excited to talk about outer space. Anyway, without further ado, here's Satoki to tell us about his research on black holes.
I'm Satoki Matsushita, working at the Academia Sinica Institute of Astronomy and Astrophysics, just research fellow. I'm doing the primary investigator of the Greenland Telescope Project and also the representative of Event Horizon Telescope, EHT Taiwan.
I started by asking Satoki about his work.
Mainly three topics. One, science. That about the black hole, how to feed the black hole, what's the effect of the black hole to the surrounding environment, those kind of things from the big scale to really small scale. That's the science part. Another is the sort of engineering technical part that the telescope, currently we have telescope in Greenland and engineer make the telescopes, but it's not really science ready. Where the telescope is pointing is unclear, or how the surface is very smooth, or those kind of thing is unclear. So we do those kind of tests and make a telescope to the science ready telescope.
And what exactly are you doing now?
Mostly management, which is unfortunate, but young people does the science, and someone have to do those kind of management.
No,
as a top of the project that have to manage this kind of thing to make it all the people work comfortably. And of course, myself is that, as I mentioned before, that the make a telescope better. But recently, COVID avoid us to go to the site. That makes it a little bit difficult. But if the travel is okay, then I go there to make telescope again that the science quality and actually observe for the Event Horizon Telescope and other project and do the research.
Is the Event Horizon Telescope, this project, and mapping out that picture of a black hole, is this the biggest project you've been a part of?
In terms of the international sort of single project.
Okay.
International collaboration, it's really worldwide because we have to collaborate with telescope all over the world. And each telescope belongs to each institute or universities, and we collaborate together to observe that black hole at the same time.
Right.
The exact same time for like several tens of hours for roughly like 1 week. So that we have to coordinate all the single telescope. They have each project for each telescope.
Right.
And they are observing several other things. But at that time, stop everything. We only concentrate on the Event Horizon Telescope observation.
Yeah.
And then make an observation all the exact same time. That's so that it's really big international project. It's something like 350 people all over the world.
Wow.
350 people. And each telescope has those kind of several tens of people. And of course, not only telescopes, there are some theorists, what this picture means, or that's kind of how to analyze. Some people analyze the data that from the data to image, there's many complicated things that we have to calibrate.
So the reason we need all these telescopes all over the world, is it because we need the biggest possible range of vantage points to see this thing that's so far away?
Yeah, so probably people can understand bigger the telescope, you can see more details. But the telescope itself cannot be too big. That so far the biggest telescope in the world, movable, steerable telescope is 100 meter. On the ground, no moving. Like probably you saw the old 007 movie that the 300 meter telescope in the Puerto Rico, that was 300 meter. Recently it's broke down. Well, that was 300 meter, but it's not steerable. And recently China made the 500 meter, that kind of telescope. But that's the so far biggest, but that regulate the size. So if we want to see more details, then we have to put telescope far away, either on the cable or set the hard disk or something and record it and later analyze the data to make it far. Well, for example, Greenland and Chile, it will be 9,000 kilometers away. But if we can correlate those kind of data, then it's comparable to the size of the telescope, like 9,000 kilometers.
Right.
So that's why we can see really, really detail, which we never saw in the past.
Right. And it takes these all over the world. And this is as the Earth is spinning and you have to take all of this data into account?
Yes, that makes only the true telescope. Then that it's two telescope. But if it's rotate, then make it more area to make it like 9,000 kilometers away, but it only 2 points, but makes it more like an area kind of thing. And if you have more other telescope, then it will fill up the gaps between. That makes like big telescope.
How many telescopes were involved in the total project overall?
That time that the image, the black hole image, people knows that at that time it was 8 telescopes, but that was 2017. We observed 2017 and from 2018, our Greenland Telescope joined and well, the COVID screwed up everything, but 2021, 2 more telescope joined. So, currently 11 telescopes.
Okay.
Yeah.
And this project is ongoing.
It is ongoing. So
until forever, I'm sure, because we're never going to understand. But the observations continue to observe this same black hole, or are you moving around in your observations?
So far, we know there are 2 black holes we can probably image. One is the M87. That is we imaged actually. That is the first one we came out. And second one is that the black hole in our center of our galaxy, that the Milky Way galaxy, there's a black hole too. But those 2 are we think we can image, based on the past research. And so far, we only showed the picture of the M87 black hole.
Okay.
Yeah.
M87 is much further away though, right?
Much further away.
It's a silly question, but I'm wondering how far away is that?
Actually, okay. 5,500 mega light year away. Oh, I forgot. But the thing is that it's far. So that M87 is 1,000 times further away compared to the center of our galaxy. But the black hole itself is 1,000 times heavier. It is same as relation with the distance and the size.
The mass?
The mass.
I noticed that you said lighter and not, or I'm sorry, you said heavier and not bigger and lighter and not smaller. Is that because you can only measure
that's how it actually can see? Okay, black hole physics.
Its size, is it when we see it, is that directly related to its mass always?
Yes. Sort of black hole physics is that the heavier, bigger, linear relation.
That seems to make sense, right?
1,000. Well, but for human, bigger doesn't mean,
Right, okay.
Heavy.
Okay, yeah.
But it's really that the heavier, bigger.
It's the straight linear correlation.
Linear correlation. So that the 1,000 times farther, then that the size of the things getting 1,000 times smaller, right?
Okay,
Well, like a paper. This paper, that if you put 2 times away, then the size is 2 times smaller. Same, that the black hole 1,000 times far away, it's 1,000 times smaller, but it is 1,000 times bigger.
Right.
So even far away, and our Milky Way galaxy black hole is closer, but the apparent size is almost the same.
Okay.
Just a coincidence. Just a coincidence. But
just a coincidence.
Yeah.
Okay. And how do we know this? I want to know how we know this. I'm afraid this interview will be 5 hours long. So.
Well, the size itself is that, again, that the thing I explained that if you move the telescope further, you can see the detail. But in the past, there was a study with a much less number of telescope. And that tells already we couldn't image at that time because it's too less, only 3 telescope at that time. So that we couldn't image, but we can roughly say the size should be around this or smaller or something like that. Yeah. So that from there, we know roughly it was sort of very blur that it should be around this size or smaller. But like if you see the telescope with some or whatever, that if you use smaller one, you can see bigger, but it's a blur. But if you get bigger and bigger telescope, it's getting sharper and sharper, but still blur. But still, you can start to see the size of the thing. But whether there's a shadow or not, we couldn't tell it in the past.
Right, yeah.
Yeah, but finally, 2017 observation, we use 8 telescopes so that we could image and we could see the shadow at that time. Yeah, so that was the sort of story. The light, it's from the X-ray or gamma ray, optical, infrared, and radio wave. And what we are using is a radio wave. Well, here we are at the sort of radio.
Yeah, we're using radio waves here too. Yeah.
So that the FM is 100 megahertz.
Okay.
Roughly, that when you tune 100 megahertz.
Wait, I'm taking notes. Okay, yeah.
100 megahertz. And we are using 200 gigahertz. It's about 1,000 times the different wavelengths or frequency. That the megahertz, 1,000 times bigger will be giga.
Right.
So that the 200 gigahertz, that's the frequency we are using. And that's the telescope. It's a parabolic telescope, not the like optical,
right.
Put into the eye. So we cannot see, actually.
Yeah.
But with the antenna, we can detect. Like same as a radio, that the this kind of AM radio is 1,000 kilohertz, FM 100 megahertz.
Whoa.
We use 200 gigahertz. Yeah, that kind of thing.
Man.
Sorry, it is difficult. Sorry.
It is. No, I love it. I just have to take a second to think. And actually, I've been asking you so many questions to your face. I forgot to ask the questions with paper.
No.
So.
But the radio is very, well, this radio or this kind of only voice is very difficult to explain those kinds.
I'm sure it is, yeah. If you can't move your hands around and say, this is how big a black hole is.
or picture or something like that.
Can you tell me about your work with the Greenland Telescope Project exactly?
Actually, I am the principal investigator. Means that the top of the project. So the one difficult part is that the management, scheduling, also get the money for the project.
Right.
So write a proposal. I want to do this kind of thing. So please give this amount of money or those kind of thing. And also that we need to do the observation maintenance so that they arrange those kind of schedule and time with all the engineers, scientists in our project. And of course, myself does those kind of observation. And first I mentioned about to make the telescope to the science quality. Those kind of thing always make the telescope better and better. So those kind of thing I am doing for the project.
Moving on to sort of what the work is like. How many people are on your team?
About 30. Well, some people do many things in parallel, but they are roughly around 30. Yeah. Both engineers and scientists, between 30 and 40. Yeah.
Where is a lot of this funding coming from? Which government or multiple around the world?
Actually, this one is mostly Taiwan, the Academia Sinica and the Ministry of Science and Technology of Taiwan. And the smaller part, we collaborate with the Smithsonian Astronomical Observatory in US. So mainly Taiwan, operating this Greenland Telescope Project.
And what makes Greenland specifically such a good place for this?
So, as I mentioned, that to observe details, we have to put somewhere telescope far away. Far, the better for the resolving. Which means that if there's a other telescope there, then there's no point. It's so that we have to find out somewhere far. But another thing is that the sky have to be very clear in terms of this 230 gigahertz, 200 gigahertz frequency, which is that the water vapor is the most annoying thing that absorbs the light from the astronomical source and also disturbs the light. So that we want to go somewhere less water vapor and there's no telescope. So if you think about it, one of the best low humidity site is desert or really cold place that all iced out, or really high mountain, or combination of those. And there are telescope in South Pole. There are telescope in the Chile Atacama Desert, which is 5,000 meter high, and Hawaii, top of Hawaii, it's a 4,000 meter high. And actually, another that collaboration of Smithsonian, that we have the sublimeter array and collaboration with the East Asian countries. We have the East Asian Observatory there, that James Clerk Maxwell Telescope. And so that the Hawaii there's Chile there, South Pole there, and where's the other place? Where is the very cold or very high or combination of those? And we found out Greenland. Yes, the name is Greenland, but it's actually covered by the ice.
Right, yeah.
Yes, and the top of there, it's 3,200 meter high and just ice, like South Pole, just ice, nothing other than the ice, so that the humidity is really low. So, and there's no telescope so far. So that and also that the distance from the like Chile or Hawaii is that the 9,000 kilometer, which is sort of the other side of the Earth, which makes really better resolution than the others. So that's why we decided, okay, let's put the telescope at the Greenland.
It fit all the requirements that you were looking for. Now, what about the crystal, the frozen water in the atmosphere? Doesn't that affect it too, or? Actually,
there's not much, actually.
Oh, okay.
Rather that, like, when it snowed or the right mice filled in the telescope, that's sticking the telescope, that's more annoying part. So that we make the heater on the backside of the telescope to a little bit higher, 1 degree high compared to the outside. Then there's no right mass pulling in. So that kind of thing, we do that. And then it is actually much better than the other sites.
What kinds of technology and equipment do you use?
The telescope itself is a parabolic telescope that the sort of we call antenna. So the its size is 12 meter diameter, and it's movable. That the telescope itself is sort of, if you think about the those kind of parabolic antenna, it's something that looks like that. So antenna itself is like that, but the detector, we use the technology of the superconducting technology. That the detector itself is that we call S.I.S, semiconductor-insulator-superconductor heterodyne receiver. That so that the semiconductor part is that current can move around, but the insulator is an insulator. There's never current cannot move around. But with that the quantum physics, that the tunnel effect, if there's some energy came in to the detector, then the tunnel effect makes the current movable from between jumps from the semiconductor insulator semiconductor, that the jumps from that gap, so that it can actually detect the light, and only some specific frequency we can detect. So the engineers make that kind of detector that specially tuned to observe 200 gigahertz. And we use that technology, and so we can detect 200 gigahertz frequency from astronomical source. And that since superconducting technology, we need to lower the temperature to 4 Kelvin, which is zero Kelvin is the absolute code, but the only 4 Kelvin. So that that kind of receiver, we have to install it on the telescope and always working on. Yeah.
What is the setup process like for focusing on an area of space?
I would say the accuracy too, that it comes accuracy, because if telescope 9,000 kilometers farther away, then the time have to match with the really 10 to the minus 13 second accuracy or something like that, which is really high accuracy. So that those kind of calculation, we can do that. But how to make it that accuracy is also another technology we need. We use the atomic clock that is so far the highest accuracy clock. And all those time information also recorded in the hard disk and sent out to the some we call correlation center, and match all the telescope to the that accuracy level. Then we can get a correlated data set.
And then you still have to account for the distance between places on Earth also has a little bit of space-time delay. Is that a thing? Or is that too small?
Not the space-time delay, but the accuracy of the distance of the telescope with the probably a few tens of micrometers scale. If it changes, it goes to the sort of time delay, also similar things, but the position change, time change, that makes the all the data shift together and makes the data corrupted, so that we have to measure those kind of things. Everything have to be as accurate as possible.
Yeah.
Yeah.
And for the picture of M87,
yes.
What was the period of time over which you took all of the recordings? It was like a few weeks or something?
Actually, one image is 1 day, sort of 8 to 12 hours. But we observe for roughly 1 week, 10 days. So we have the different image for sort of different days, and each day have their own image, but almost the same. A little bit of the difference, yeah.
So for a project this big, do you know exactly what you're looking for when you begin the observation? Or sometimes is there something you find out by accident and have to?
I think both. Of course, for the this kind of study is long term. That from early 70s, 80s, some other people start observing like M87 or the center of Milky Way, as we call Sagittarius star. That are the sort of well-known sources. So many people study for long years, decades of study. Then we start to know, oh, this should be the something we may be able to observe and image it if technology exists.
Right.
But some black holes that they accidentally found out, oh, this is maybe something interesting that we may be able to observe. But so far we haven't find out that kind of thing. For imaging the black hole, so far only M87 and Sagittarius star. For this case, that we know that the Sagittarius star, the center of Milky Way galaxy, and M87 is the two sources we may be able to image. That's why we made the collaboration, and everybody think this is reasonably and convincing, so that let's do it. And that's why all over the world, all the telescopes agree to collaborate each other to make it happen. And actually, it happened.
You talked a little bit about your current project, what you're working on now. What's next?
Currently, the telescope is located at the Greenland, but it's not the summit of Greenland, but only at the sea level. We call the Thule Air Force. Actually, it's inside the U.S. Air Force Base, because they have the power, they have the flat land, and actually all those shipment goes to that Air Force Base. So we could ship from the US to the Greenland Thule, and sort of top of the Greenland it's really just ice, so more danger. So that it's better to put at the sea level. There's place to stay. The power also exists, so not as harsh environment as top of the Greenland. So that we can test many things that whatever we made is really avoid any problems, like it's even minus 30 degree, minus 40 degree Celsius. Well, actually Celsius and at low, that the Celsius or Fahrenheit, it's minus 30, minus 40 Celsius.
Right, yeah.
Yes. Well, that cold environment, everything have to move any problems. But on the other hand, it's sea level, so that the water vapor is much more. So if we move to the summit of the Greenland, then we can do much better, higher frequency, like 300 gigahertz, 600 gigahertz, or like higher frequency, then that we can see much details. So far, we saw the black hole is at a very blur. So that we want to make it more sharper and sharper image to resolve what's actually going on around the black hole. Is something falling in? Is something coming out? It is the first time to see the black hole image, so that now we want to study further how it looks like if you see sharper, or if you see the different black hole, how it looks like. Those kind of things. This field is started, so that we want to continue to understand what's going on around the black hole.
When you look at a black hole, can you see the traces of something that has fallen into it?
We think so.
Okay.
That's what we want to see. That's why we're pushing further and further. Yes.
But watching traces of things that fall into black holes is important in understanding what exactly.
Well, first, that the basic question is whether Einstein's theory of relativity is correct or not for the gravity. That's one thing. So far, no.
So far, so good, Mr. Einstein. Yeah.
So there's no violation that the Einstein is correct. And so whether it's even really close to the black hole, really heavy things, is that still correct? Or something different physics comes in, or those kind of things. That's the first basic questions. And others is that how to feed a black hole. If something go in, the black hole should go around. Or if black hole is spinning, what will happen to the outside? Then that if black hole spinning, then that the space time around the black hole is also dragged by the black hole spin. So if something is moving around or coming out, if we could see those kind of things, but so far we haven't seen that. So we want to see what is going on around the black hole. That's which we also want to see. And we know that the M87, that we call astronomical jet, some very sharp things coming out from the black hole, but we don't know how. We think that that is related to the black hole spin to take out the angular momentum that something have to go out, but that's just so far just a theory. So we want to see how black hole spin makes the things move out. If something going in, we cannot observe anymore, so that we can say that it's gone. And whether it comes out, I don't think we can prove it.
And Hawking radiation, is that the radiation that comes out?
Oh, that's or
is that really, another hour of the maybe
that's really tiny part, only at the surface part. So I don't think we can see it with the our observation.
Is there any other work that you're doing or work that you're involved in or work that you would like to do or that is being done on Earth or off Earth that you want to talk about?
I think so far I'm concentrating on the Greenland Telescope and the Event Horizon Telescope, and because it's, as I said, that it just started, and another at least 5-10 years, we will definitely put effort on this to make it better and better understanding for the what's going on around the black hole, and after that, so far I want to go is that make better resolution image. And see how really black hole look like. Yeah, it's so blurred. That picture is so blurred. We want to see much sharper.
What happens when we put a telescope on Mars?
I think it's too far away. So that
too far away.
Too far away.
So it's too hard to make the exact calculations then.
No, actually, that Mars is probably even Moon because it's too sharp. That you can see so detailed thing is that getting darker and darker, so that as far as it's so sensitive, huge telescope, it's just too difficult to see it. So I think the satellite may be the good selection choice to make it reasonably detailed. With the probably what we think is that the signal is strong enough to detect with the current technology. That so that if you go too far away, its current technology is too less sensitive to detect something useful. So satellite project will be the one of the thing. Although whether Taiwan can do it, that's a different question. But.
Right. And you're working in Taiwan specifically. Were you sent here? Was this part of a project, or you wanted to be in Taiwan specifically?
Actually, the reason why I come to Taiwan is at that time, this Event Horizon Telescope Project doesn't exist. And before that, I was working at the Hawaii, the sub-image array that I was belonged to the Smithsonian and as a postdoctoral fellow. And that was collaboration with the Smithsonian in Taiwan. And the Smithsonian worked for 3 years. Then my 3-year contract finished. But that telescope was the world's first sub-emitter interferometry that can do the detailed study at the well, it's 230 gigahertz, 345 gigahertz, and 600 gigahertz. Those kind of very high frequency astronomy research. That was the world first at that time. So I wanted to continue this one so that Smithsonian finished. Then I go to the other collaborator, which is Taiwan. So I came to Taiwan to continue this project. Then the next project, ALMA, which is Atacama Large Millimeter Sub-emitter Array, that is in Chile. So far, that's the biggest sub-emitter interferometer in the world. And the construction started. So I belong to Taiwan and I went to Chile for 1.5 years to make it again, make the telescope from the engineering level to the science quality level.
To the right specifications? Okay.
Yes, yeah. Then at that time, Greenland Telescope Project started in Taiwan, so I joined this project.
I didn't connect that before, that it is in Greenland, obviously, but it's Taiwan's project?
It is Taiwan's project because Taiwan, there's no good site for doing the...
that makes sense. And there's a lot of humidity. Humidity here, yeah.
Too humid, yes.
Right, and a lot of humility too. So good job, Taiwan. How did you, on your personal journey, how did you become interested in science? Do you still remember?
Oh yeah, well, definitely it's because my father is the physicist.
Mm-hmm.
Yeah, so that when small child, that he brings to the science museum or planetarium or bring to the camp place watching stars together or those kind of things. So that from small child, well. My father loves nature and science. That makes me love nature and science. I think that in terms of science itself, it's my dad. Yeah, that's one thing. And also the other thing is that when I was a child, elementary school, actually, because of my father got the sort of 2-year job in New York. So whole family moved to New York for 2 years.
Wow.
So in general, that in Japan, the elementary school classes are taught by the same teacher for the whatever science, literature, gymnasium, whatever is same teacher teach everything. But when I moved to the US, well, my father didn't have the money to go bring me to the Japanese school, so that I just go to the public school in New York.
Right, those international schools are expensive.
So it's very expensive, so that I just go into the public school. And well, my big surprise was that science teacher teaches science, the music teacher teaches music, and the teacher of the class only teach some very small number of classes. And at that time, my elementary school, public school, has the science class. Inside the science classroom, there's a planetarium. And at that time, Voyager 1 and 2 reached to the Saturn, Jupiter, and the first space shuttle launch. So that there are so many space things, and the science class only teaches space. And it was wonderful for me. I don't have to learn about like life science or
chemistry,
just space. I was so happy that then I really get into the science around that time. And after that, after I come back to Japan.
Where in Japan did you grow up?
Actually, I grew up in Sendai. Northern part of Japan, Honshu, yeah. And around junior high school, again, my father connect to the Sendai Astronomical Observatory, that the public observatory. And the director at that time, Osaka-san, there's a sort of citizen astronomy club or something that that after Friday night, after astronomical observatory close, then that Osaka-san, he's the director of the public astronomical observatory, and he opens to those clubs so that we could use the telescopes of the observatory, or someone brought in and we could use it. And so every Friday night, and some elder person teaches how to observe moon, how to observe galaxies or those kind of things. And so every Friday night, I went with my friend, my oldest friend, even now. Every Friday night, go there and do the all kind of astronomy things. And
That's
love
awesome.
it. Yeah, that was really nice. And that how I learned that how to operate the optical telescope, or where's which star exists, which galaxy exists at where, or those kind of things.
And how you learned to operate a tripod, which you helped me set up before the interview. Yeah,
exactly.
That's awesome. You're speaking to my heart here, because I love space science more than anything too. It's rare that we get to report here on, reporting the news on the radio, that we get to report space news. But every time we do, I get to say and next in extraplanetary news or something like that. And it's so fun to talk about the next rocket launch or news from the space station. Even recently, man, I stuff like, a Russian space crew sent a director and an actress to space, and they're going to film the first movie in space.
Before Tom Cruise, yes.
Right, before they beat him or so. I don't know. I'm here in Taiwan. I don't really care who wins. I just want to see movies in space. So with real space physics, yeah. But yeah, learning about this kind of stuff is so fascinating, because there's almost no other science that is studying just what is on this larger scale.
Yeah, that's true. That recently one of the hot topic is that the astrobiology, whether now we saw that the many planets rotating around many stars, and people are looking at the habitable zone, which is at some distance from stars. The water could be not ice too far away, it will be ice. Too close, it will be water vapor. Our Earth is located at around the sun, which is water is in the liquid status.
Right.
That's why the life exists, so that the people are looking at whether those kind of planet exist at the outer space, whether the planet possibly in the liquid state, or try to observe the atmosphere of the planets, that including oxygen or those water or those kind of things. Now it's a very hot topic.
So I guess my next question is, with the power that we have of all these telescopes all over Earth to focus on points so far away, I know it's a lot of work and funding to get them all to focus on the same place, but are we going to be focusing on any exoplanets?
I'll say that many telescope exists, but some telescope, the light has so many wavelengths that some are observing at X-ray, some are observing the optical, what we can see, some are observing the infrared, and each frequency or wavelengths has the different topics of research. So currently if we want to image black hole, 200 millimeter submillimeter wave is the only way to really image the black hole, because that is where we can resolve the black hole. But if we want to study about for example, that the exoplanet, probably optical or infrared is the best study, because those kind of things, those kind of information we can see for where the planet exists, and how far distant, or those kind of things from the infrared radiate the temperature of the planet, or those kind of thing. And water vapor is very dense around there, so that there's no point to concentrate on everything into one topic. I think each topic has different wavelengths, so that I think that's also sort of healthy, that the many research exists all over the world, and many people interested in many things in a different field, so that I think those kind of differentiate is also important, I think.
What is the most difficult part of working in your field?
I'll say currently it's a technology that makes it better and better. That's my feeling, that the science itself, many theorists already predict around black hole should be like this or should be like that, but they cannot regulate which is true. But that's the only observation can tell that this one is the truth. That is actually different or something like that. So to make it observe, then technology is the key point, that to make it make that observation possible, then that the technology is the important point. And well, Taiwan has those kind of technology now, so that I think we can go further and further. That's why I also stay in Taiwan. That Taiwan, in terms of this radio astronomy field, Taiwan is one of the top runner in the world. So that I'm happy with this.
So what do you see for the future of cosmic science, astrophysics in Taiwan?
For the radio astronomy, I think that we can go further and further to make it better and better, interesting output. That we made it possible to see the black hole, so that make it more sharper and more details. I think Taiwan can do it. In terms of bringing the telescope to the space, I'm not sure. That one, to make it much further, I'm not sure. But the space technology is getting more and more popular in Taiwan, especially like Formosa 7, 8, those kind of satellites. It's working now at the outer space. Mostly that is for the Earth science, but if we move that toward the space science, maybe possible. But that is a little bit decade later science.
What kind of training would someone have to go through if they also wanted to work in this field?
I would say it depends, but if you want to do the research in terms of like black hole or astronomy, then 3: physics, math, and English.
Mm-hmm. English makes sense, yeah.
Yes. But if you go toward the technology side, then some electric engineering, those kind of thing comes in. But basics would be physics and the math is the two basic thing that which definitely needed.
And is there anything else you'd like to say to the people of Taiwan?
I'll say that as I mentioned, that this project is supported by the government and the academic Ministry of Science Technology, which comes from all the tax from the taxpayers. Taiwanese people pay the tax. That's why we could do the budget come to our project. So I say thanks to all the taxpayers in Taiwan.
Thank you, Taiwan. Yeah.
Thank you very much. And well, so that what we can do is that show all those exciting results. And also other thing is that the technology, as I mentioned, that the technology now in Taiwan is one of the forefront runners. But like 20 years ago, Taiwan didn't have this technology. But decades later, because we did a lot of project that both science and technical side make the science better, but technological side make the technology better and make the Taiwan grow. Not only our institute, but the companies in Taiwan that makes those kind of instruments or the technology or the big things that also grew up from the really beginner level to the forefront level. So that that also very important. Both science and technology works. That's why we we can do the world forefront research, not only science, both science and technology. And that's, well, I'll say that all those Taiwanese people work for these companies and the technical part, universities, our institute, other institutes. And with all of the support, we could do this kind of research, this kind of thing, thanks to Taiwan.
Yeah, thank you, Taiwan. What are you most proud of?
I'll say, as I mentioned, that the MIX telescope bring from the engineering level to the science level. I did for the SMA, ALMA, GLT, those kind of Taiwan-related project to make it those kind of science level. And that's makes all the other astronomers, researchers use those kind of telescope producing the science. And I did many of things that that I'm proud of. Not only me, of course, but with the help of others. But I did those kind of things I'm living in Taiwan for 19 years.
Wow.
And considering those kind of things to make it Taiwanese telescope to the scientific world, first-class scientific level. And I'm proud of it.
Much respect also to all of the people who have worked on all of these projects, because it takes really like the whole world's best scientists to really make these things happen. So thank you for being a part of that.
Oh, thank you very much.
Once again, all my thanks to Satoki for educating me on outer space. I've provided some links to his work and past projects in the podcast description. And there's even a documentary about the Event Horizon Telescope on Netflix called The Edge of All We Know. It's worth checking out. Anyway, thanks so much for listening. In the meantime, I'm off to read some more Wikipedia articles on black holes. So until next time, I'm Trevor Tortomasi on ICRT FM 100. If you'd like to hear more from ICRT, you can check out our other podcasts. We've got Taiwan This Week, a roundup of the news in Taiwan every Friday, English in the News for useful English expressions explained in Chinese, and EZ News, spelled with the letters E and Z, for simplified daily news. For some lighter news in both English and Chinese, check out News Bites and News for Kids. And if you enjoy them, tell a friend. Thanks for listening.